Hello and welcome everybody to the MATLAB and Simulink Racing Lounge. In today's second part of our episode Modeling Physical Components, we are going to talk about data-driven or data-based approaches for modeling. Before jumping into that, let me quickly recap what we've done in part 1 of the episode. So we've introduced you to modeling using a simple suspension example. We have highlighted that some modeling approaches are purely equation-based, purely mathematically rigorous derived, and others are data-based, data-driven. In the first part, we have mainly talked about mathematical modeling, so means modeling from equations. We've derived a mathematical model in Simulink for our suspension example. We have also introduced you to a second language, the Simscape language, which we can consider as component-based modeling. And let's say as a transition, we have introduced you to lookup tables, which are using data, but they can be implemented in equation-based modeling. Now in part 2 of our episode, we will talk more about modeling from data. We will introduce you to two key concepts. One is parameter estimation. Second one is system identification, which are both quite powerful tools. And last but not least, we will wrap it all up. We will critically think about our approaches and where they can be applied best in the key takeaway section. So let's move on and enjoy the second part of the episode with Sebastian Castro and myself.
Now I want to show you parameter estimation. So let's introduce what it is first.
Exactly. As far as I remember, it was the stuff when you have, well, the equation somehow at hand, but you don't know so much about the parameters, right?
Right.
Okay.
So here we have a combination of an existing model. It could be equations with Simulink, or it could be a component-based model, like you see here with Simscape.
Whatever, yep.
But the problem is that you don't really know what the parameters are. For example, as you see here, maybe you have the masses of your car and your wheel, but you're not quite sure what the spring or damping coefficients are.
Okay.
So all you need is an initial guess, hopefully one that's good enough, and combine that with some experimental data that you can collect or get from a data sheet.
Okay. Well, that technique for me seems a bit to be like optimization, right? Is it optimization happening behind the scenes?
Yeah, you've seen these slides before, so indeed it is optimization. Exactly. So what's happening here is that what you're doing is you're simulating the model with some parameters. You're seeing how good the data is being matched, and if it doesn't, then the tool will change the values of the parameters, simulate again, and hopefully converge to some better results, like we see on the right there.
Well, and now I know why you mentioned that you should have a good guess about the unknown parameters, because if they are very wrong, or if they are far off, optimization might take a lot of more resources.
Yeah, well, optimization, that's one of the things. It's very powerful at solving problems that we can't solve, but you're never guaranteed to get an answer or even the right answer.
Exactly.
So we recommend, running lots and lots of optimizations to make sure that maybe you have some kind of consistent result that you're converging to.
Yeah.
So I want to show you how this parameter estimation stuff works. So I'm going to bring up a model. You see that this one does not contain any inputs or outputs. We're going to get them from collected data. And what I'll also do is I'm going to load some preloaded data that I had, which is found here in this car data file.
Okay.
See that as I load this, I get different variables like the time at which I collected my data. I also get profiles for the motion of the car, the motion of the road, and so forth. So I'm going to use this data for my parameter estimation. Oops. So from any model, you can go to Analysis, Parameter Estimation, and that will bring up a parameter estimation tool for that model. So we have to do a couple things. First of all, we need to tell the tool which parameters do we want to optimize. So to do this, I'm just going to quickly select my parameters here. And you see that I get a menu telling me all these variables, and furthermore, which block they're being used by. So that's very helpful for large models.
Yeah, right.
I'll select my damping and my spring coefficients, and hit OK.
Well, assuming that the mass of the car and assuming that the mass of the wheel is pretty much known.
Right, for sure.
Which should be the case, right?
Yep. So I can set different initial guesses here. I'm actually going to change them a little bit. I want to show you what you can do here. So here's our initial guesses of 1,000, 1,000, 10,000, 10,000.
Yep.
Just to speed things up, I'm actually going to make these initial guesses 100,000. A lot of zeros. Oops. And something else that's very useful to do to help the optimization is if you expand any of these, you can actually configure minimum and maximum values. And that's something where I can use maybe some information I have to constrain my parameters. For example, I might want to say that I can't have a negative spring rate, so definitely minimum of 0. And just to avoid getting huge numbers, I'm going to set a limit to all these parameters to be 1 e to the 6 or 1 million.
Okay. Well, and basically you do all that in order to avoid that the optimizer is running into certain areas that are completely unrealistic.
Exactly, because I could get into situations where my values are going to be just way too large or way too small, and I do want to avoid that. So once I've configured these, should be good. Okay. All right, so that's one part, our parameters. The next thing that we need is the data that we want to load. And to do that, I will create a new experiment here. And what the experiment is doing is it's asking me to enter some data for the outputs and the inputs of my model.
It means referring back to the test data you have just loaded to the workspace, right?
Right. So you see as I mouse over this, it tells me I should enter, or one of the ways I could enter the data is by entering a 2-column information where the first column is the time and the second is the actual data.
Okay.
So here I'm going to set up the output, which is the time in the first column, and then the displacement of the car in the second. And then here I'll set up the input, which is the time again, and then the velocity of the road.
Yep.
So to see how my model is currently doing with the initial guesses that I set up, I'm going to click this plot and simulate button, which will run my model with those variables that I had.
Okay.
It'll just take a little time to finish simulating. So here you see, I'm just going to hit OK, that I don't quite have a match between the measured and the simulated data.
Okay.
So this is what I want to fix with optimization. So before we run the optimization, I'm just going to quickly add a plot, which will be very interesting for us.
Okay.
Which is called the parameter trajectory. So it's going to show us how the parameters change as the optimization is running, which is very cool.
Yep.
So at this point, there's plenty of options that you can set over here in the cost function and options.
Okay.
But for the purpose of this presentation, I'll use the default options. Just know that you might have to change some of these, especially for more difficult problems.
Well, we are getting some response from the student community that we should do an episode on optimization. And I think we can cover that at a later point about all the numerics behind optimization. But it's cool. Just use the default here and let's see what happens.
Yep. So here on the left, we have a cost function that with the iterations, it's going to hopefully go down. In the middle plot, we're going to see how the response changes as we change these values. So you see it's already taken one iteration here.
Okay.
And it looks a lot closer. And on the right, you see the trajectory that our parameters are taking as the optimization runs. You see, it takes a little while.
Basically, we all know the model complexity because you've introduced us to the model. How long do I expect to wait until this is finished?
Well, that depends on so many things, right? Yeah. It could be the algorithm you're using. It could be your initial guesses may not be very good for the model. It could be, if your model takes longer to simulate, this tool actually has to simulate the model quite a few times. You'll see here, there's a column here labeled F count.
Yep.
This is the number of times that the model has been simulated so far in the optimization. And you see that right now, just as we've spoken, the model's already been run 63 times.
Okay.
So it could take a while.
Okay. Well, I think it would just be fair to let the users or the viewers know what kind of computer you are using, just to get a feeling of, performance versus model complexity.
Yeah. So I'm using a not so new laptop.
Okay.
It's not super powerful. I have a Core i7 processor.
Okay.
However, these optimizations for a model simple like this one, they wouldn't take very long. For more complicated ones, you could pull from other resources. For example, you can tie your optimization with parallel computing.
Yep.
And you can take advantage of computing clusters and all these fancy things.
Okay. But seems that we have reached our optimization goal right now.
Yep, it looks so. So our cost function went down from about 1,000 to 7.
Yeah.
And the reason it stopped is because you see the cost function did not change much near the end.
Yeah.
And if you look at our measured versus simulated data, it doesn't look very bad at all.
Mm-hmm.
The last thing we can do is take a look at the parameter values that were chosen.
Okay.
So let me just go back over there. And you'll see that they're not going to be the same parameters that we had. They might not be the real parameters, but they work.
Okay.
So here you see you have our damping coefficients of about 4,000 and 5,000.
Yeah.
And then our spring constants are both around 100 to 200,000. And that seems to work very well for us.
Yep.
So at that point,
are they updated automatically in the workspace? Yeah, seems so.
They are. Yep.
Okay. Perfect.
So then what you can do is take these and save them, or you can even use them to run further optimizations.
Yep. Okay. Perfect.
So, yep. So that's our quick overview to that.
And I think, as far as I remember, we have one scheme or one technique left. Why not moving to that one?
Yes. So this technique is the one that you want to use when you have no idea what the equations are.
No clue. Okay.
So again, parameter estimation, the first thing we had here is that it assumed an existing model. And all we're doing is changing the parameters.
Yep.
But if you don't know anything about the model, I'll just skip forward here to the next slide. You can use system identification, where it's kind of a similar process in that you start using experimental data.
Okay.
So the same input-output relationship. But instead of having an existing model, you do not know what the model structure is.
Okay.
So here's where you get to play around with your computer and really try different approaches. For example, can your model be represented as a transfer function or as a state space?
Yeah.
Or do you need to incorporate nonlinear effects into your model? So you have to kind of try different types of model structures. And as you combine these two, you can use estimation techniques or system identification techniques to try fit a model to your data.
Okay. Well, at that point, I'm really curious about the strategy I should employ there. Well, if I have no clue about my model, how can I be sure that, for example, a state space model will work or won't work? So do you have some tips about how to make that decision?
Yeah, I think the biggest tip is to start simple.
Okay.
So that would be Occam's razor for those of you familiar. That the simpler answer.
The simple solution is always more often the right one. Yep.
Yeah. So what you want to do is start with something linear and not too complicated. Something like a state space with only a couple of states. And you might try out different options for that. But if you find that a linear model is not doing the job for you, then you can start looking at other more complicated models.
Okay.
So again, you want to try the simple stuff first, and if it doesn't work, then you add more and more, and see if you get led to the right direction. But just like optimization, this is one of those methods that has a little bit of an art to it. So you do need to just try all sorts of different things. You need to make sure you're collecting the right data that covers a lot of the frequencies of your system, for example.
Yeah.
So it's a lot to try out, and just want to run you through a quick example of that.
Exactly. I would have asked you for that. Would be interesting to see how it works.
Great. So I'm going to clear everything just to start fresh, and I'm going to reload the same card data that I was using for parameter estimation. And what I'm going to do here now is, instead of going to Simulink, I'm going to go into the Apps tab here in MATLAB, and you'll notice that depending on which tools you have installed, you might have an entire section here for control system design and analysis. And I'm going to be using the system identification app here, which comes with the system identification toolbox.
And of course, we have made sure that the system identification toolbox is part of the Formula Student software offer. So feel free to use it.
So yeah, I'll just bring up that app. and you'll see a window that looks like this one.
Okay.
Where the way you're going to run through this is you're going to import some data into here, and then as you move to the right, you're going to actually get models that are estimated.
Okay.
Instead of talking to you through it, maybe we'll just do some identification. We all learn by actually doing here. So I'm going to import our data as a time domain data, and I'm going to enter the workspace variables that I have here.
Exactly.
So in this case, as my input, I'm going to choose the xRoad variable, that is the position of the road. And as the output, I'm going to choose xCar, which is the position of the car. I'll name the data, just leave it with the default name, my data, and make sure that I have the data sampled at the same time that I collected the data. That is, I start at 0 seconds, and I'm using a sample time of TS, which you see is here as 1 millisecond.
Okay.
And then I can import this data. It comes up in my system identification app, and I can view it in a time plot if I want. So here I see the relationship between my input, which is a kind of noisy random signal, and we compare that with our output. So hopefully a random signal is generally a pretty good one to try capture dynamics because it contains various frequencies inside of it. Another common one is, for example, a step response or pulses. These are good ways of exciting the right dynamics for your system. So once you have your data, you see it immediately gets dragged into this working data here. And before we do the estimation, we can actually pre-process our data. We can do things like removing the means. We can filter our data. We can split or merge different experiments. We can do all sorts of things. But we'll stay simple here and just use the one piece of data that we have.
Okay. And well, then we have to make the decision about the modeling type or the theory behind, right?
Yeah, and that's the hard part, right? So when you hit estimate here, you have all sorts of different models.
Okay.
You
Let's
have
go
things
simple.
ranging.
I think following your advice, what is the most simple thing we could do here?
Yep. Well, the most simple is going to be a linear model. So that's going to be either a transfer function or a state space. These are two that are very common. So I'm going to choose a state space.
Okay. Why?
I'm going to choose it, first of all, because state space models are always linear, just because they use linear matrices, linear matrix approach. And secondly, because you get a lot of information as to what's going on inside the system, because you get access to states, as well as just input and output, like a transfer function. So you see I have a lot of options here. The most clear one for state space is the model order, or the number of states. And I could either choose an order myself, or I could use this other option that says pick the best value in my range, where it's going to look through orders 1 through 10 and tell me which one might be best.
I would pick that because I have no clue about the order I should estimate.
So I'll just warn you that this is not necessarily perfect, and you really should try other things.
Okay.
So here you have a plot of model order selection. I'm not going to get into the details, but basically this tells us what is the additional information that I get from adding another state to my model.
Okay.
So it's suggesting me to have one state, because when I move to 2 states, I lose, or I don't gain that much more extra information.
Okay. Yeah.
And then as I move from 2 to a higher value, I don't seem to be getting much more. So I'm going to try insert. I'm just going to select the column that says 1 and say insert. That's going to open up this estimation thing. And if I just go back, I see that I now have a model here on the right side.
So quickly? I would have guessed that it takes a similar amount of time as the optimization. Why is it so fast?
Well, the reason it's fast is because this is a bit more of an analytical approach, where it looks at the data and it fits it once. If you remember, the optimization actually runs the model multiple times and makes small changes to your parameters, and then runs again and again and again. This is just a one-time optimization.
Okay.
So what I can do is I can compare my model with my output. I'm just going to bring that up. And it seems that the tool wasn't, its heuristics or its criteria for evaluating things may not have been ideal. You see that? Our model doesn't precisely match. So one thing we can do at this point is we can try adding more states, let's try, for example, the two-state system.
Whether it makes it better. Yep.
I'll insert that, re-optimize, and you see I get a little green line here. It looks a little better, but it could be better, right?
Yeah, yeah.
So let me go all the way up to 5 and insert. And you see that I am not gaining very much by moving to 5 states.
But still, we have had no clue about our model. We didn't have a model, and now are able to have a reasonably good relation between inputs and outputs. So if you have nothing, that's definitely worth a try.
Yep, sort of. So here, the score that you see here, basically, if you can get it to 100, it means that it's a perfect fit.
Yeah, okay.
So it looks like the best model that we had was the second one we did with the 2 states, which has a 71% score. We can always do better. I just want to show you this because it is an art. There's no one solid answer. Yep. But besides just the model order, there's plenty of other estimation options that I can choose. For instance, I know just by playing with this model myself that I can change this to a different algorithm called prediction error minimization. And I'm also going to uncheck this for allowing unstable models. I do not want an unstable model.
Yep.
So I can change all my options, and I could try model order selection again with the new algorithm. And here I'm again going to drag a order 1 model with this new algorithm, and also an order 2. So now I have 5 models in my workspace that I have all on top of each other.
Well, and number 5 seems to be pretty good. 19?
Yeah, so number 5, I really like that. I'm very hopeful about it.
Yeah, yeah.
So maybe this is the one that we want to use because it's such a good fit. Another way to play with this then is to test it. So I'm going to take the system 5 that I had here, and I'm going to drag it to the workspace. And what I've done is I've created a test model that will compare the real model that we had with our estimated system.
Okay. Well, that's interesting because
load this up.
That allows us really to qualitatively compare that. That's good.
Yeah, so there's a really great block called the LTI system block.
That directly relates to that, okay.
Yeah, so I can take that SS5 model that I had here and just enter its name in that block.
Okay.
So I'm going to enter that SS5. And now I'll compare that with our real model, which if you look in here, it's the Simscape network.
Yep.
And let's see how they both compare with our sinusoidal input.
Okay.
Oh, they're very close to each other.
Okay, there's a signal behind the purple one. Okay.
Yeah, you see that. Maybe I can move this around. You see that there's a little bit of a mismatch, but it's not bad at all.
Exactly.
Maybe we'll zoom in some more. So this model does a good job. Of course, if we tried other models, we might not be as lucky.
Okay, well, for sure. What I really like about that method, it can help. It can help you out in a tricky situation. What is a bit, it feels like magic to me because the process of obtaining the results is not very rigorous. At the end, you said, well, it's playing. It's using some models, trying different orders. But nevertheless, in that case, it actually is helpful. But well, my comment on that would be careful with that. I think as it's not so rigorous, you really should take care about every step you do, and perhaps some literature research on the underlying basics would not harm.
Yeah, one of the things that we want to highlight here is that we were just using a single data set. So we took this data and we put it as our working data, and we made sure that our estimation was as close as possible to this data. But another very good thing to do is you see that at the bottom here, there's a validation data set. So what people usually do is they'll collect 2 completely independent sets of data. Then you'll have one estimation set, which you'll use for creating the model, and then you'll test it against a completely different validation data, just to make sure that you haven't overfit your model to just one experiment.
Well, and this actually can create some confidence in the model if you take random data and compare it to the parameters you just obtained.
Definitely. So you can do this both with the parameter estimation and with system identification.
Okay.
I would certainly look into using validation data if you have multiple experiments.
Okay, great. So Sebastian, I feel that this episode has been quite intense. We have taken also quite some time, but I feel that it's very, very interesting for the student teams. I think, sadly, we have to move to the key takeaways already. what I'm going to do is I'm going to read through them and then ask you to comment a bit on them and comment a bit on the learning outcome of today's episode. Well, first thing, there are many types of modeling. That's obvious. We have seen at least 5 of them, and also combinations are possible. Some require equations, some do not. Well, that's something that is obvious. So we started with mathematical rigorous formulations and then ended up with estimation techniques. And, well, multiple approaches can be combined. Good. Well, from my point of view, that's pretty straightforward. Can you enrich that with a bit of your profi tips with your experience?
Sure. So really choosing the model approach takes, I think there's 2 main things that you want to consider.
Mm-hmm.
First of all is how much do you know about the model?
Mm-hmm.
If you know quite a bit, if you have all the physics behind you, then you can get a most accurate model by actually doing the math and creating a mathematical model.
Mm-hmm.
But if you have something that would be very difficult to model or maybe impossible,
Mm-hmm.
then some of the data-driven approaches can help.
Okay.
You can think of, for instance, Christoph, you used the example of an engine earlier on,
Yep.
where there's a lot of very complicated thermodynamics and mechanics in there.
Mm-hmm.
But what you can do is you can provide an input to the engine, you can measure the outputs like the torque and the speed, and
Yeah.
you can use that collected data to estimate perhaps a simple but good enough model
Yep.
for your system. The second thing, which also affects the modeling approach, is going to be how much detail do you want?
Mm-hmm.
For example, if you're modeling, let's say, an electrical system like an inverter
Yep.
in the motor,
Mm-hmm.
you could model all the individual semiconductors and you get a very detailed, very accurate model.
Mm-hmm.
But electrical components are very fast. So
Yep.
if you try to integrate that into a big model of a car driving for, 1 hour,
Yeah.
then the small time scale of your electronics is going to really slow down your simulation. And it might be way too much detail for what you need for a large-scale system simulation.
Mm-hmm.
So at that point, you can use some of the data approaches to create a simplified behavioral model
Mm-hmm.
that just approximates the behavior of your electronics, and it gets you a faster simulation for the whole vehicle.
Okay, perfect. Well, this the last point really was helpful. So can we summarize it like that? Can we summarize it like that? So always try to be on the left side of the bar, so more to the mathematical approaches as possible. Well, if it's not available, you have to start with data-driven approaches. And secondly, what I get out from your statement is, take care about CPU time. Because,
Yes.
if you always want to go for the mathematical rigorous approach, you might lose a lot of your CPU resources.
Right.
Okay.
And, nothing is stopping you from having a switch that for certain simulations you use the detailed one, for other types you use the simpler. So it's up to you to decide what works best for you.
Okay, well, these were very helpful comments on that. Sebastian, thank you very much for putting together a lot of this material. Thank you for guiding us through. Thank you very much at that point.
Thank you for having me, Christoph.
Cool. One promise that we are going to make here, so all the models you have prepared for us, and we will put it on a file exchange, so that
Absolutely.
guys watching the episode can actually try it right away. This is very good. Thank you very much, Sebastian, for preparing that. And this brings me definitely to the end of today's episode. Again, if you want to see more videos of the Racing Lounge, just go to the mathworks.com/Racing Lounge webpage. There all our videos are hosted. And if you want to get more information about Formula Student, just go to the dedicated website of your competition, which is mathworks.com/FSG for Germany, FSUK for Formula Student UK, and others. Then, as I've said, we are really interested in your feedback. As you know, we have the team email address for that. So if you want to have it private conversation, just go there, formulastudent@mathworks.com, and drop us a mail. What we've done recently, we have created a Facebook group page. Also, Sebastian is already a member of that. And if you feel that certain questions are, meant for public, you want to share your comments, you want to share your questions, we really encourage you to use that medium. And the page is called Racing Lounge, MATLAB and Simulink Racing Lounge. Really looking forward to the discussion happening on that page. And on that bombshell, it's time to end. Thanks for watching and see you next time.